Welcome to this explainer, everyone. To design the perfect pressure vessel, engineers rely on this almost magic concept called allowable stress. And the crazy thing is, behind all those massive, complex design codes, it's actually just based on some surprisingly intuitive physics. Once you grasp this foundational principle, you're literally getting the exact same perspective that engineers use to safely manage these massive, high-pressure facilities. Let's get right into it. If you've ever walked past a refinery or chemical plant, you've definitely seen those towering pressure vessels, right? And inside those tanks, highly volatile fluids are boiling at unimaginable temperatures and pressures. So how in the world do engineers guarantee, with absolutely 100% certainty, that these massive steel giants won't just tear apart like wet paper? I mean, they can't just blindly make the steel walls thicker and thicker. Cost and efficiency make that totally impossible. Well, this is exactly where the ultimate engineering safety net comes into play. It's called allowable stress.
Okay, let's dive into this. To really understand allowable stress, we first need to lock down two foundational, twin-like concepts, stress and strain. Now, stress is simply the physical force applied to a material from the outside. Strain, on the other hand, is the result. It's the actual physical deformation, like literally how much the material stretches or compresses because of that stress. So it's a direct cause and effect relationship. The force you apply, that's the stress. The resulting change in shape, that's the strain. And that brings us to the famous stress-strain curve. Honestly, this graph literally changed the history of engineering. If you look at the y-axis right here, it tracks the stress, basically how intensely the force is being applied. Meanwhile, the x-axis across the bottom maps the strain, showing you exactly how much the material actually deforms. So starting right at 0, as you apply more force, the line climbs steeply. Tracking this trajectory is amazing because it reveals the entire lifespan of a material. It shows us exactly how it reacts under pressure, all the way to pinpointing the precise moment it ultimately fails and just snaps. To intuitively understand this curve, just think of a simple rubber band. That first part of the graph, the straight line before it bends, we call that the elastic region. In this zone, it's just like stretching a rubber band. If you pull it and let go, it snaps right back to its original size, right? When the stress is removed, the material returns perfectly to its normal state. But what happens if you cross that line? I mean, we've all pulled an old rubber band way too hard and it just kind of stays permanently stretched out. Well, that is the plastic region. Once a material enters this zone, removing the force doesn't do a thing. It's suffered permanent deformation and is never, ever bouncing back. So you're probably wondering, where exactly is the tipping point between that safe elastic region and the damaging plastic region? Well, we call that the yield point, or yield strength. This is the exact specific moment the material yields, or basically surrenders to the outside force. In plant engineering, yield strength is absolutely crucial. It is the ultimate boundary line. If a pressure vessel is subjected to stress that crosses this line even slightly, well, it might still look completely fine to the naked eye, but at the molecular level, critical and permanent damage has already occurred. There is literally no going back. And this brilliantly illustrates the engineer's clear goal. For the entire decades-long lifespan a pressure vessel is in operation, it has to be meticulously designed to stay safely within that elastic region. It must stay securely below that yield strength boundary. Because, no matter how aggressively the pressure fluctuates inside that tank, the material just has to flexibly handle the load and return to its original state. For sure, that is the only way to guarantee total safety over the lifespan of the equipment. But here's the thing, simply saying, hey, let's design it safely just isn't enough. I mean, if every engineer out there had their own personal definition of safety, it would be a total disaster. And that is exactly why the ASME code exists. Created by the American Society of Mechanical Engineers, this code acts as an unbreakable set of rules. It basically translates the physics of our stress-strain curve into strict, highly accurate safety standards. The ASME code gives us the exact step-by-step regulations for determining our big target value, the allowable stress. Okay, so how exactly does the ASME code tell us to calculate this allowable stress? Well, if we look at Section 2, Part D, engineers actually have to calculate two distinct formulas. Formula 1 takes the tensile strength, which, remember, is the ultimate maximum strength right before the material completely snaps in half, and divides it by 3.5. That creates a massive built-in safety margin. Then, Formula 2 takes the yield strength, our boundary line for permanent deformation, and multiplies it by 2/3. By running both of these calculations, engineers establish incredibly conservative baselines against both the material breaking completely and the material permanently warping. So the crucial point is the one golden rule of this whole process. Between those two calculated values, you always choose the smaller value. Now, you might be wondering why intentionally use the lower number. Well, setting a lower allowable stress forces the entire design to be much more robust. It essentially compels the engineer to use thicker steel plates or stronger materials to handle the intended load. Choosing the smaller value means you're basing your design on the more vulnerable failure point, and that, my friends, guarantees maximum uncompromising safety. So allowable stress is our ultimate shield, right? It ensures these pressure vessels hold their shape and don't just burst under immense loads. But here's a thought for you. This perfect calculation really only applies to the material at its current normal temperature. What happens when extreme temperatures of 200 or even 300 degrees begin to fundamentally alter the properties of the metal itself? How exactly does our trusty safety net hold up when the heat rises and the material physically weakens? Well, that's a whole different puzzle, and we'll uncover the answer to that in our next explainer. See you then.